Greetings everybody, and welcome back to another abstract algebra video. In the previous two videos we took a look at some basics of rings, and now we're going to start taking a look at how to create new rings. And this video in particular we're taking a look at the polynomial rings. So before we get into that, I do want to make a few remarks on notation, or rather some definitions. So let R be a ring, and we're also going to take some element A in the ring R, and we're also going to take some integer n. Now sometimes we want to have repeated addition of this ring element A. So if you want to, you can write this as A plus ... plus A, but n times. But this is a little bit cumbersome to write out all the time, so usually we define the notation n times A, and I'm going to put this down over here for reasons you'll see in a second. So you do have to be a little bit careful though, because this multiplication, that's not the multiplication in R. And it's pretty clear why it's not multiplication in R, because this n here, this guy, is not an element in your ring R. So this is merely notation that we define here to represent these sorts of expressions. So this expression works if n is greater than 0, because you just have repeated addition n times. Now how about if n is less than 0? You can define something almost similar. You're still going to have a plus together a bunch of times. How many times? Well, it has to be negative n times, because n is negative, and it only makes sense if you do repeated addition, well, positive number of times. But because n is negative, what you do at the very end over here is you take the additive inverse of everything. So you have this big ring element here, you put a negative sign out the front, that's the additive inverse. And then finally, if n is equal to 0, well, you just define this to be 0. It's nice and simple. So you have something of the form 0 times a equals 0. Hey, we might have seen that before. You might have recognized that from the previous video. But you have to be careful, because this 0, this is the 0 in the integers, whereas this 0, that's the additive identity in the ring R. So these are two different zeros here, and this is still not the multiplication in R. It's still this multiplication that we just defined. In fact, once you have this over here, then some of the usual properties you might expect from such an operation definitely work. For instance, if we have n plus m, so these are two integers here, so the whole thing is an integer, and you multiply that by a, well, this is repeated addition of a n plus m times, but that's the same thing as repeated addition of a n times, and then plus repeated addition of a m times. And also you have something kind of similar for multiplication as well. If you have n times m, so this guy here is an integer, and then you decide to multiply this into a, then what you can do is you can take m times a. So now this guy is a new ring element, it's repeated addition of a m times, but then you take the result and you multiply it by n. So if you have repeated addition by m times, and you take everything over here, do repeated addition n times, well, that's the same thing as doing repeated addition nm times. In fact, if you know a little bit about modules, the way we define this multiplication action actually defines something called a z module on the ring R. So basically you can define what it means to take a ring element and then multiply it by an integer. So we're going to cover modules later on in the course, maybe in a few weeks, so don't worry if you don't understand what that means yet. Now you can also do something similar with repeated multiplication. Sometimes you want to do repeated multiplication to a times n times. And you can simply define this expression a raised to the n to be equal to, well, this guy here. Well, this works only if n is positive, but if a has an inverse, then you might be able to extend this to negative numbers as well. And of course, just like before, the usual exponentiation laws that you're used to using this notation carry over as well. Okay, so this was some notation that I just want to mention, because we're probably going to use it again later in the course. And actually, we're going to see a bit of this when we do some polynomials as well. So let's get into that now. So, polynomials. Let's start with a definition. Let R be a ring. Then we define this new set, which we call R adjoin X, so we have square brackets here. It turns out this is a ring, so it's the ring of polynomials with coefficients in the ring R. So from one ring, we can create a brand new ring. So to have a ring, first of all, we need to define what the set is. So as a set, what does this guy look like? R of X is going to be the set of objects of the following form. We have a0 plus a1x plus a2x squared plus ... plus anx to the n, where each of these ai's, these guys are ring elements, and also n has to be a natural number because polynomials can only have finite order. We're not working with power series or anything like that, although I will mention power series later. Now these x's we're adjoining here, these have a special name. These are called formal variables. So these aren't necessarily variables that you can substitute numbers, let's say, into it, although we can think about each of these polynomials as functions. These x's here serve more like placeholders at the moment for the ring elements. So I like to think about this x as simply a placeholder at the moment. A nice way to think about these polynomials at the moment, instead of thinking about them as functions like you usually do, is you can imagine each polynomial is a clothesline. And on a clothesline, obviously you're going to have, well, your clothes hangers to hang your clothes on. So you have like the 0th position, the 1st position, the 2nd position, and so on. And you also have the nth position over here. So each of these positions you hang a clothes hanger on, and each of these clothes hangers carries a ring element. So you have the A0 hung on there, and you have the A1 hung on there, and then so on. So each of these polynomials, you can think about them as a tuple of ring elements. So it's simply a way to collect a bunch of ring elements together into one. And of course this tuple, it's ordered and it has a finite length. So I just want to mention another thing about this set R of x, because it can be a point of confusion if you see it for the first time. If you write R of x, this is referring to the set of polynomials in R. So it really contains all polynomials that you can think of, which means that you have to have finite degree, where the degree of a polynomial we're referring to this highest power here. It's a bit of a subtle point, but this doesn't mean that there's a bound on the degree of a polynomial. Doesn't mean that we're limited to some, well, arbitrarily chosen n value. Sometimes, however, you might see people write Rn of x, and this is the set of polynomials with degree at most n. But you do have to be careful with this, because this guy is no longer a ring, because a ring has to be closed under multiplication, and if you have two polynomials that you multiply together, they might give you a polynomial with even a higher order, which might not be in this set. So sometimes you might see this notation here, but you do have to be careful because this guy isn't a ring anymore. Whereas the usual R of x is a ring, because no matter if you have a really large degree, two polynomials of really large degree, if you multiply them together, it's still inside of the set because the degree of that resulting polynomial is still finite. Okay, so this is the ring of polynomials, it's R of x. We have the set. I also need to tell you how to add and multiply polynomials together. And the formula for doing so are as you would expect from high school. So here's the addition of two polynomials. It's fairly straightforward, you just add the corresponding coefficients together. So if you think about these clotheslines over here, you add the 0th positions together, the 1st positions together, and so on. And as for multiplication, you want this to respect the usual way you multiply polynomials together that you've seen in high school. So if you have two polynomials of degree n and m, they don't have to necessarily have the same degree. This is going to give you a new polynomial with a degree n plus m. So now we have n plus m coefficients, and there's actually a formula for these coefficients. So if you take the ckth coefficient, this is equal to the sum running from j equals 0 to k. You take your aj and you multiply this by b of k minus j. So now that we have addition and multiplication defined on this set here, this makes R of x into a ring. Well, not quite yet technically, because I still have to show the axioms, but you can trust me that the axioms work out. So from one ring, we now have a brand new ring, the polynomial ring over the ring R. So future Q and Cubes 3 here, I just want to add an extra, rather important remark, I guess, before we continue. Let P and Q be two polynomials in your ring R of x. Then from your polynomials knowledge in high school, you'll know that the degree of P times Q is equal to the degree of P plus the degree of Q. However, this is not true in general for rings, and I'll give you an example of that. Consider the polynomial ring z mod 4z, but I take this guy and I join x, so it's the polynomial ring over the integers mod 4. And we're going to take p of x to be equal to 2x plus 1, which lies inside of this polynomial ring. Then we have the degree of p, that's equal to 1, it's a linear function. But if you take a look at the polynomial, but squared, well, that's 2x plus 1 squared, but that's equal to 4x squared plus 4x plus 1. But hang on a minute, 4 is equal to 0 inside of this ring. So these terms over here, they're going to vanish, leaving you with exactly 1. So the degree of p squared is equal to 0. So this degree formula over here doesn't work for general rings. Actually, it only works over rings that are called integral domains, which means you don't get this behavior where two non-zero elements multiply together and they give you 0. So it's just something to be mindful about when you're working with the general rings. As I mentioned before over here, these x's that we have, these are formal variables. You can think about them as placeholders for these ring elements. So these x's are not necessarily going to plug anything into them, but you can think about each polynomial as a function from R to R. So each polynomial, p in your ring R, also determines a function from R to R. Now technically I should probably use a different name here like p bar or something, but I'm just gonna abuse notation and say this is a function from R to R. Now notice over here I'm using p to denote the name of the polynomial. Usually if you do working out with p, for example if you want to multiply p by an x for instance, then I would put a p of x over here, but it's over here because I'm just trying to refer to some elements of the polynomial ring. I don't really put p of x here, although you can if you want to. Some people do that just to make it extra clear, but I'm a bit lazy, so I just write it like this. But if I do working out and I mix x's into the equations and whatnot, then I usually put an extra set of parentheses just to be clear that p is a polynomial and not just some random constant. So how does this function work over here? Well, if you let p of x be equal to a0 plus a1x plus dot 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 plus anxn. So this is just some random polynomial in the ring R of x. Then, well, as you would expect, if you try to evaluate it now, if you think of p as literally a function in this case, and you evaluate at some ring element R, then this is just simply a0 plus a1r plus dot 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 plus an r to the n. And we know exactly what r to the n means because we already discussed that at the very start of the video. And obviously r to the n is a ring element, an is also a ring element, so their product is a ring element, and you're adding a bunch of ring elements together, so everything on the right hand side is definitely going to be inside of your ring R. In fact, the act of evaluating your polynomial at a particular ring element, this has a special name. This is what we're going to be calling the evaluation homomorphism later. You write this as EV of R, evaluated at P. So it's basically applying this ring elements to your polynomial. And it has some special properties which we'll discuss in one of the future videos as well, after we've taken a look at ring homomorphisms. And I just want to add an extra remark to this section. If you have two different polynomials in your ring R, these may actually determine the exact same function from R to R, or in other words, the exact same function in the ring of functions from R to R. So what I mean by different polynomials in this case is that if you take a look at their list of coefficients, the lists don't exactly match. So to see an example of this, we're going to consider the ring of polynomials over the field of two elements. So this is f2 of x. So f2 of x, if you don't remember what that is, that's just the set with 0 and 1. There's only two elements in here. And we're going to let f of x be equal to x, and we're also going to let g of x be equal to x squared. And both of these lie inside of f2x, the polynomial ring over the field with two elements. So clearly, f is not equal to g inside of this ring. But now if you think about these polynomials as actually being functions from R to R, well, there's only two possible inputs you could give these functions. It's 0 and 1 because we're working over this field of two elements here. So let's take a look at this. F of 0, that's equal to 0. You have g of 0 is equal to 0. F of 1, well, that's just 1. And g of 1, that's 1 squared, but 1 squared is also equal to 1. So therefore, what can we see from this? We see that f and g are actually identical when you think about them as functions from R to R. Or in this case, it would be f2 to f2. Okay, so what we've managed to do so far is to simply construct the polynomial ring, and we can also think about these polynomials as functions from R to R. I'm going to finish off this video with an extension of this idea. In particular, I'm going to talk about polynomials in more than one variable. So far what we've been able to do is we've taken a ring R, and from this ring what we've been able to do is we're able to adjoin this element x to it, and this gives us a brand new ring R of x. So this guy was a ring, we also have a ring over here. Well, what happens if we repeat this? What happens if we start over here now, and we adjoin a different element, let's say? Well, nothing's stopping us from doing that. Let's adjoin another element, let's say y. And what we end up with is R of x. This is our original ring, but then we're going to adjoin this element of y. And obviously it still holds that this is a ring. And sometimes you write this guy as R, adjoin x and y, just so you don't have to have brackets everywhere. So R adjoin x and y is an even bigger ring now because it's going to contain polynomials in x. In fact, you can think about polynomials in x as constant and then y as being the variable. So obviously you have the inclusion that R is inside of the ring of polynomials because you just identify R with the constants, but R of x is also going to live inside R, adjoin x comma y, and also R of y lives in there as well. So if you want an example of what objects in this ring would look like, well, it's basically combinations of x's and y's everywhere. So you could have, for instance, x, y, this guy is in R adjoint xy. This is also in the ring R adjoint xy. And basically, it's all linear combinations of elements of the form x to the a and then y to the b. Okay, and why stop with the two variables? Why don't we keep going with this? It's definitely possible. So you can keep going with this until you reach the ring R adjoint. You can have n variables, let's say. So this is even a bigger ring now. And well, you might as well keep going with this. And it can consider adjoining, well, infinitely many variables. x1, x2, and then dot dot dots. All these guys down here, these are still rings. And while we're on this topic of creating even bigger and crazier rings, I might as well talk about formal power series. So you saw that in the ring of polynomials, there was a condition on the degree of the polynomial. Namely, it has to be finite. Well, obviously, it's because they're polynomials. They have to have finite degree. But what you can do is you can define the so-called ring of formal power series in X, which you denote with double square brackets. And this is defined to be the set of objects of the form A0 plus A1x plus A2x squared plus dot dot dot, where all of these AIs are ring elements. So notice, I don't put an end to this. This can keep going for as long as he wants. And he might be, well, a little bit concerned about this sort of expression because this is a power series. You would want some kinds of convergent on it, wouldn't you? But it turns out, because we're only working with formal power series, these x's, remember, they're merely placeholders. They're not necessarily going to be variables that you plug things into. It turns out that no convergence is required for this. Because we're just thinking about this as a list of ring elements, we're not thinking about these objects as functions. Although if you do want to have some notion of convergence, then the very least you need is some kind of topology on your ring, which, well, that's an additional structure you need that we don't have at the moment. And obviously with this ring over here, you have the inclusion that your original ring of polynomials lies inside here. This is just a much, much bigger ring. And if you want to be fancy, you could probably have formal power series in multiple variables as well, but we're probably not going to see formal power series again. This is just a fancy example just to show you all the crazy sorts of rings you can build just from having just one ring to work off. So that's going to be all for this video on polynomial rings. We've covered quite a bit, so hopefully you guys enjoyed this video. In the next video, we're going to be taking a look at the ring adjunctions, which is how you can add new elements to your rings. So that's all for today. Hope you guys have a wonderful day, and I'll see everyone in the next video.